Okay, great. Okay. So shall we start? Okay, fine. So vortex motion. So in the vortex motion, I think so lighting I'll adjust. Yeah, I think so lighting is better now. Okay, so vortex motion. So till now actually whatever we have discussed, that is a two-dimensional and axisymmetric flow. So there actually the motion of the fluid is completely potential kind. So potential kind we mean if there is a potential difference between the two different places. So this is one place and this is another place. So if there is a potential difference, obviously this potential difference will cause the fluid to move in this particular direction, provided if it is having more potential energy at this particular point. So these 2 points actually will make the fluid to flow in one particular direction, and this motion we call as the potential flow. So this is the potential flow. But so now actually we are entering into a different kind of motion, that is the vortex flow. Vortex flow, in general, a fluid will flow in two different directions. That is, one is the potential and another is the vortex. These two together will form the generic motion of the fluid. So here, what is this vortex flow? Vortex we mean a kind of curl. Curl means, so in the water, right? So you can notice that there are some curls that are rotating in the water, creating a hole in the middle, right? So audio is not clear. Okay. Okay, let me change the mic once. What about you, Keshav? I think so Anand says it is clear. So I think I have shifted the room. So this is a big room. Maybe that is the reason actually why there is a noise. Just a minute, I'll open the windows. Okay. Is it fine now? Okay, great. Now see, so this is the potential. And then suppose if there are some curls that are happening, curls means it will try to rotate the flow like this. And then there will be a big hole in between, right? So this is what we call as the vortex. So this is what is called the vortex flow. So in the vortex flow, the same fluid element will try to rotate like this. Now in general, a fluid flow causes both the potential flow and the vortex flow together, right? So this is a generic flow of fluid. Will contain both vortex and potential flow together. So these two together actually it happens. Now, so a vortex is nothing but wherein del cross Q, if it is not equal to 0, then we say that the flow is of vortex kind. if del cross q is equal to 0, then we say, so the flow is of potential kind. Because for any vector identity, del cross q is equal to 0, then q can be expressed as minus del phi. So q can be expressed as minus del phi. So this is the reason why we call this as the potential flow, where phi is the velocity potential. And the flow is called as potential flow. And the flow is called as the potential flow. Got it? Okay, note down this. So this is the case actually what we are going to deal with now. So this one actually two-dimensional and axisymmetric flow, we dealt it already. And axisymmetric flow. Two-dimensional and axisymmetric flow. And this is the flow, this is the vertex flow. So there are some rotational components that are present in the fluid. So when there are rotational components that are present, obviously del cross q will not be 0. This is what we call as the circulation. So there is a kind of rotation in the flow. So that rotation is nothing but the circulation. So this is modeled as a complex potential for us now. Okay, note down this. We are going to model this as the complex potential. Noted down. Okay. Now, so in case of circulation flow, so the circulation is happening like this. And then this flow is due to del cross q not equal to 0. Right? So the circulation, right? So usually actually we represent the circulation. So you know that, so Stokes theorem says that integral f dot dr is equal to, so in a closed line integral, now this will be equal to the area integral del cross f times dot ds. So this is the Stokes theorem. Now this dot del cross f, right? So here actually our case actually q is nothing but f. So q dot dr over the closed contour C is equal to double integral a del cross q dot ds. This is how actually we use the Stokes theorem to find out the circulation. So this is what we call as the circulation of the fluid. So ideally, if del cross q is equal to 0, there won't be any circulation. That's exactly the reason actually why the fluid will go in a linear motion, and that's what we call as the potential flow. So because there is a potential difference exists. Now here in this case, del cross Q is no more 0. Hence actually the circulation can be found with the help of Stokes theorem. So Stokes theorem relates a areal integral to the line integral. So if you take one particular line like this and then over this entire line, how much circulation that is happening, that can be found with the help of the area of this particular circle. So the areal integral for del cross Q, if you apply, this will give the total circulation, and this is usually represented with omega. Got it? So this is how you will find out the circulation. Note down this. Done? Now, so here actually, earlier actually the stream function in case of a normal flow, so this is how the stream function which will be represented by psi. Now here the stream function is in a circular fashion like this. So this is the stream function, and the stream function actually will try to move the flow like this. Now in this flow, so at any angle actually if you can take out, so this is actually let us say x-axis, then at any angle theta you can take it. So across theta, or if theta is equal to constant, that is the line, it will be cut by the fluid lines, right? So all the fluid particles will cross this particular line and then go in a circular fashion like this. So that means the radius across, so along the radius there is no flow, correct or not? So along the radius, there is no flow, or the Laplace equation with respect to radius will vanish. Why? Because see this, so del square phi equal to 0, del square phi is equal to 0 for a potential flow. Similarly, del square phi is not equal to 0 in case of a circular flow. Now here, but it should be equal to some constant value. This is what we call as the Poisson's equation. So this is what we call as the Poisson's equation. The same Poisson's equation is getting satisfied even with del square psi is equal to rho. So both will get satisfied the Poisson's equation because there is a presence of circulation. But here the thing is, the potential flow will lead to the horizontal flow, but the circular flow will lead to the circular flow. But the condition of the flow direction and the potential field direction, both will be completely perpendicular to each other always. That means if you try to model this as a potential, the potential difference will be created along this particular line, correct or not? So for theta 1 to theta 2, there is a potential difference. So that means the potential value is dependent on theta, correct or not? So phi can be modeled as some constant into theta, some constant lambda into theta, and then the potential is always in the negative direction. That is, from higher potential to lower potential, the fluid particle will be traveling. That means the potential can be modeled for this as minus lambda theta. And the other thing is, the streamline can be modeled as if like potential in case of normal flow. Got it? Those streamlines, that means these streamlines are traveling along the direction of the circle. So that means the Laplace equation del square dou square by dou r times of dou psi by dou r. I'll just write it del square psi in polar form with only radius variation. It will be dou by dou r of 1 by r times r into dou psi by dou r. So this is the polar form, and this is equal to 0. So this is the derivative with respect to r. So that is, if you notice here, the streamlines are only in the circular fashion. Now if I take with respect to the radius direction, is there a change in the value of psi? If you take along the radius direction, there won't be change with respect to the radius, because across the radius, that is, the radius is like this and the fluid flow is like this. So if you take the derivative with respect to r, then definitely it is going to vanish. So because the flow is in the circular direction. So if you integrate this, then this will be dou by dou r of r dou psi by dou r equal to 0. If you integrate this, r times of dou psi by dou r equal to constant, and then dou psi by dou r is equal to lambda by r, and if you integrate further, psi is equal to lambda log r. So psi is equal to lambda log r, and this is the function in case of circular flow. This is the potential function in case of circular flow. So these two together will form the complex potential. So complex potential W can be written as phi plus I psi. So phi is minus lambda theta plus I times of psi is lambda log r. This is how we model the complex potential. Now if you take I lambda common, I lambda if you take it out, then this will be I theta plus log r. I theta plus log r. This can be further written as I lambda times of, so theta can be written as e power I theta log of. So this will be log r plus log e power I theta, or that can be written as I lambda times of log r e power I theta, and then I lambda times of log z, since z is equal to r e power I theta. Z equal to r e power I theta. So this is the polar form representation of the complex number. Now this is very crucial for us. So in the entire discussion, the key point what you need to take out is W can be written as I lambda log z. Now I am going to analyze this. First you note down this. Done? Noted? Yeah, so it will be linear with respect to theta. Exactly. Got it? So the complex potential of a vortex flow will be W is equal to I lambda log Z. So this is the complex potential. Now what is this lambda? So lambda is nothing but the constant, right? So the circulation over one closed loop of the fluid, so circulation is treated as K. So this is also called as the strength of the vortex. I explained this. So this is the strength of the vortex is nothing but the circulation value. So the circulation is nothing but the K. So K is nothing but over the angle 0 to 2 pi. So this is the line integral, right? So this line integral value will be, so minus 1 by r times of dou phi by dou r times r d theta. So this is a line integral, right? So you are taking along the line of one particular circle like this. That means this entire periphery. So that entire periphery dr by d theta, and this is nothing but the velocity component, right? So the velocity component with respect to the radius. So minus 1 by r dou phi by dou r d theta will be the circulation along this particular line. Got it? So this actually, so this value, from where we got this? So del phi, so is equal to minus dou phi by dou theta, dou phi by dou x into I minus dou phi by dou y into j. Now the same thing if you put it minus del phi. So this is what we call as the velocity. So Q. So Q can be written as minus del phi minus dou phi by dou x minus dou phi by dou y times of j. This is in the Cartesian coordinate. Now in the polar coordinate, so Q can be written as, so del phi minus del phi, but del you have to express in polar. So polar form minus dou phi by dou r minus 1 by r dou phi by dou theta. Yeah. So this is minus dou phi by dou r into r cap minus 1 by r dou phi by dou theta into theta cap. So this is the velocity components in polar form. Yeah, that's correct. So this is dou phi by dou theta. Yeah, dou phi by dou theta. Right? Now this is r will cancel. So integral 0 to 2 pi minus dou phi. So this is nothing but 2 phi, and this is the k value. Yeah. So this is minus dou phi by dou theta into d theta, right? So dou phi by dou theta, so phi actually is equal to minus lambda theta. So this is the potential flow. So dou phi by dou theta can be written as minus lambda. So if we replace it here, so lambda times of d theta integral over 0 to 2 pi. This will come as lambda 2 pi. So this is nothing but k. From this, lambda can be expressed as k by 2 pi. So this is the intended relation. Got it? See this. So here actually the complex potential actually omega times of W is equal to I times of lambda log Z. This is the complex potential. In the complex potential, this lambda value is a random constant we brought in. This random constant value we were able to express in terms of the strength of the vertex, that is K. So K is nothing but the circulation. That circulation we also call as the strength of the vertex. The circulation value we can find it out by taking the component of the velocity, that is this component of velocity q theta over the circle of 0 to 2 pi. So along this direction, the tangential component of the velocity will be q theta. That q theta you can express in terms of the polar coordinates as minus 1 by r times of dou phi by dou theta, where phi is the potential part of it. And then if you find out minus 1 by r times of dou phi by dou theta into r d theta integral 0 to 2 pi. So into r d theta, why? Because we are trying to find out the circulation over the closed contour given by this particular circle. This closed contour is nothing but the perimeter. You can give it an elemental perimeter as r times of the angle d theta. So this value r you can cancel it out, but minus dou phi by dou theta is nothing but the potential. As I told you, there will be a potential difference between these two angles. So this potential difference is directly proportional to theta. That means this is with respect to theta, it is linear, as you said. So this is dou phi by dou theta value is minus lambda, and this is the lambda component we brought into picture as a random constant. That random constant value is nothing but a lambda times of d theta. So this d theta will be lambda times of 2 pi. After substituting this, that will be equal to the strength of the vertex K. So lambda can be expressed as K by 2 pi. Now this is most generic form of expressing. So the complex potential you can write as Ik by 2 pi times of log Z. So this is the value of W in case of the vertex flow. So why we brought into this format is we are very much familiar with the two-dimensional flow. The two-dimensional flow we dealt with the complex potential, which will give the complete information for us. That information is the potential and the stream function and the velocity. So everything we will get to know, provided if you know the complex potential of it. The complex potential of a linear flow actually we have modeled. Now actually the same thing we are bringing into that format. That format is nothing but the complex potential format. So here any vortex is nothing but a rotational flow there. So the rotational flow there, we can model it as if like it is a complex potential. So we can use this complex potential value to find out the stream function, to find out the potential value, or to find out the velocity components, maybe in the radial direction, maybe in the theta direction, right? So all such kind of information we will get to know only with the help of this complex potential. So whether you understood this derivation or not, but this you need to remember. A vertex can be modeled as Ik by 2 pi times of log Z. So this is as if like a source or a sink, but the strength of the source is a complex value, Ik by 2 pi now. Earlier actually, the strength of the source actually we modeled as plus m, and the strength of the sink we modeled as minus m. But here it is a complex value. That's the only difference. But the complete analysis, whatever we made in case of two-dimensional analysis, exactly the same thing we will do even here also. Got it? Understood? Okay. Noted down? Okay. But the problems that will be given in case of this vertex flow will be very, very tough to handle in the vertex flow. Why? Because the problems in UPSC, they are going to ask actually with a lot of complexity. Not only, so they test the knowledge only in fluid dynamics. So they will be testing your ability even in analyzing the functions of complex functions, at the same time analyzing the real functions also. So that level of complexity will be given. So those are very, very tough. Actually the previous problems actually I have seen. So that is, the toughness is not understanding fluid flow. The toughness is to solve the problem. So because the complexity involved is Very, very tough. Got it? So here, okay, so let's take one case, one simple case. Here vertex. So vertex at any location, the complex potential will be ik by 2 pi times of log z minus z1, where z1 is the location of the vertex. Is the location of the vertex. And the rectilinear vertex. So rectilinear vertex, we mean the vertex is on xy plane and there is no circulation in yz or xz plane. So this is what we call as the rectilinear vertex. So normally whatever we see a vertex in any fluid, right, that is a rectilinear vertex. What it means for us, suppose if you take, this is an xy plane and this is the z axis. So this z axis, if there is a vertex, the vertex will be here like this. So this is how the vertex will be, right? Now if you notice, the axis is always z axis. So the vertex axis will be this axis and the vertex axis here it is z axis. So this is the z axis is the vertex. That means the vertex is circulation. The vertex circulation will be only on the xy plane. And these two are nothing but the rectilinear vertices. So rectilinear vertices are nothing but two vertices on the same plane. On the same plane. That is having same vertex axis is called rectilinear vertex. It's called rectilinear vertex. Got it? So that means these two are nothing but the rectilinear example. So this is an example of rectilinear vertex. So this is an example of rectilinear vertex. Got it? So usually z axis will be the axis of the vertex because we usually model this as, so depth is treated as the z axis and the plane is treated as the xy axis, right? So that's why actually a rectilinear vertices means on the water from the top, if you see two different vertices are rotating there, those two together we call as the rectilinear vertex. Now these two together, what will it do? So these two can have the same orientation or maybe a different orientation. So that's why the orientation is represented like this. So this is how actually a vertex is usually represented. Suppose if this is the line of axis and then there is a orientation like this and then there is a orientation like this. That means both are rotating in the same direction like this. Both are rotating in the same direction. Now if those two are rotating like this in the complete infinite fluid, then a fluid particle at this particular point is getting influenced by this one and this one together. Got it or not? This vertex is located at a Z1 and this location is nothing but Z2. Then the fluid potential at this particular point W is nothing but Ik by 2 pi times of, so let us say this is K1 and this is, so this is K2 and this is K1. So this is the strength of the vertex and this is the strength of the vertex K2 here, and the fluid particle at this particular point is getting influenced by both the vertices because these two are rotating. But this is located at Z1 of strength K1 and this is located at Z2 of strength K2. So these two together will influence this one. The influence will be the complex potential at that particular point. Will decide how the fluid particle has to move, with what potential it has to move. So that will be given by the complex potential of it. So Ik by 2 pi times of log z minus z1 is due to this one, and plus Ik by 2 pi times of log, so this is Ik1 and this is Ik2, log z minus z2 will be the complex potential due to this one. These two will together will give the complex potential at this point. Now this one you can simplify to separate the real part and the imaginary part separately, and that will be giving for us, that is So that will be giving for us, the real part will be the potential part and the imaginary part will be the streamlines part. So the function, so the complexity I told you, there will be a huge complexity involved in it. The complexity here it is to separate the real and imaginary part out of all these things. Got it? Being these two are only two simpler vertices, you will be able to separate this easily. But the thing is, in the UPSC, the problems that are going to ask is, there are infinite number of vertices are placed at equal distances. And some are oriented in the clockwise direction, some are oriented in the anti-clockwise direction, or all may be oriented in the same direction. In such cases, what will be the complex potential, or what will be the velocity at any point, what will be the streamlines dilation at any point, that is going to be asked. Now the concept is pretty simple and clear. So any vertex can be modeled as Ik by 2 pi times of log z minus zk. So that is the model of the complex potential. The complexity that is involved is the number of vertices that will be given, and to separate the real and imaginary part. This is the complexity, nothing more than that. Got it? Idea is simple, but the complexity is more in simplifying it. Got it? So you can note down this. This is the resultant complex potential. Done? Okay. Now we'll understand the image of a vertex. Two different cases we will try to understand. One is image of the vertex. With respect to a plane. Suppose here there is a plane. A plane boundary is present here. Let us say on this particular line at a distance of z1 there is a vertex of strength k1 or k. Then here actually if you want to keep the flow on this particular line as the surface, then you have to introduce one more vertex of strength minus k. Then the resulting complex potential at any point, let us say this is z, then this is located at z1 and this is located at z2. Then the complex potential at z will be W is equal to Ik by 2 pi times of log z minus z1 plus minus Ik by 2 pi times of log z minus z2. So here this is z2 and that is z1. So this is clockwise oriented. Let us say this is clockwise and this is anti-clockwise. That is the difference. So this is how actually we will model the image system. Now let us see whether the flow is on the boundary, whether it is tangential or not. Now this is ik by 2 pi, if you take it out, this is log of z minus z1 divided by z minus z2. Now this can be treated as, or else actually we will take one more step. Log of z minus z1 minus log of z minus z2. Then this is z minus z1, you can model this as ik by 2 pi times of log r1 e power I theta 1 minus log r2 e power I theta 2, where if you take this line, this angle will be theta and this angle will be theta. Got it? So this value will be R2 and this value will be R1. Now, if you take this ik by 2 pi times of log of R1 e power I theta 1 divided by R2 e power I theta 2. So this is equal to ik by 2 pi times of log R1 by R2 log R1 by R2 plus I times of theta 1 plus theta 2. Theta 1 plus theta 2, right? So this is ik by 2 pi times of log R1 by R2 minus k by 2 pi times of theta 1 plus theta 2. So this will be the real part and this will be the imaginary part, right? Real part and imaginary part. Now what if R1 is equal to R2? So if R1 is equal to R2, these two will get cancelled out, right? Now actually if you take one point, if these two are located exactly at the same distance, that is Z1 is equal to Z2, then obviously R1 is equal to R2 at any instant you can take out. That means this ratio is nothing but 1. So this ratio, log of 1 will come out to be 0. Now on this particular one, what you are going to get it is the psi is equal to 0. So psi is equal to 0 means there is no potential. So there is no fluid, right? So that means the fluid, whatever it is touching here, right? So that is going to vanish its flow, or else actually it will be tangential there, right? So this is how actually you can treat this as one vertex on the clockwise and another vertex on the anti-clockwise. So both are treated at exactly the same distance will form the image system of a plane. Now exactly in the similar manner, suppose if there is a quadrant like this, so there is a wall like this. Imagine there is a wall like this, then at a distance of, let us say, there is a vertex of strength k here. Then obviously, because of this wall, you can model one more strength of vertex minus k here. And then because of this wall, you have to model one more of minus k here. Now these two has to be balanced again, right? So there is no presence of wall here. There is no presence of wall here. So to compensate the potential due to these two, what you need to do is you have to model one more vertex of strength plus k. So this is the image system of a vertex of quadrant like this. So this is the wall boundary. So the boundary is in this particular shape. Earlier the boundary is exactly vertically one wall, and here two walls are there. If there is a vertex that is present here, to accurately analyze the fluid flow at this particular point, then what you need to do is you have to model one vertex here opposite sign and one vertex here opposite sign, and this is opposite to these two are exactly same as this one. You have to model as one vertex. Now all the vertexes together will form the complex potential at any point. Suppose if you want to form the complex potential at this particular point, let us say Z, then the potential will be, so let us say this is at Z1 and this is at Z2 and this is Z3 and this is Z4. Then obviously, I call this as Z2, Z3 and Z4 like this as the quadrant system. Now W will form ik by 2 pi times of, this is log Z minus Z1 and this is opposite minus log Z minus Z2 plus log Z minus Z3 minus log Z minus Z4. This will be the complex potential of this entire vortices. Got it? So this system of vertices will form the complex potential like this. Now you have to separate the real part and imaginary part, and the real part will form the potential function and the imaginary part will form the stream function. Got it? Understood the concept? Any questions on this? So whatever may be the complexity that is involved, only in simplifying this complex potential, but not to form the complex potential. So this is the image system of your wall, and this is an image system of your quadrant. Got it? So same is the case with the circle also. So exactly it follows the similar line. Only thing is you have to model the complex potential as ik by 2 pi times of log z minus zr. Got it? Yeah. So in second term, negative due to clockwise direction. Yeah. So yeah, negative is due to the directional change. So if there is a, see this, if you model this particular vertex as the clockwise, then you have to treat one more vertex at this point opposite direction. So this is an imaginary vertex you have imagined here because of the presence of the vertex here. Why we have to imagine this? Because you wanted to assure the flow on this particular wall as a tangential direction to the wall. For that, if you treat this as the normal vertex itself, then actually the flow will be completely rotational, irrespective of this wall. But what happens at this wall? So the analysis is going to be broken out there. Our mathematical analysis will be broken out at this particular wall because there is a presence of rigid boundary there. So that's why if you keep one more vertex at this particular point of opposite nature, so if this is clockwise and this is anti-clockwise, then we just proved that the analysis on this particular wall will not go wrong. That's why we call these two together as the image system. So this is the actual vertex, this is the imaginary vertex. Together will form the image system. Now here, because there are L shape of wall, so one more vertex you have to imagine here of opposite sign, and one more vertex you have to imagine here exactly same as the original one. So all these four together will give the accurate analysis of the image system completely in the presence of these walls. Got it? So only the directional change. Got it? So do you have any questions on this? Any questions? But understand that this is a very simple concept. So you have to model the complex potential, separate real and imaginary parts. So entire analysis is dependent only on that. Yeah. So with this, I'd like to stop the class for today, and tomorrow I'm going to solve some of the previous problems given based on the vertex flow.